Hello, today we're going to start the first of three videos talking about how to calculate truss forces. So this is again our civil engineering bridge truss project that we're going to look at. And so we're going to start off with just some of the basic concepts that we need to understand, some of the assumptions that we're going to make, and how that simplifies our process, but also creates a little bit of error in what we get. But they kind of go through some of those beginning things in this first video. And second video, we'll look at kind of the starting steps that you needed to go through to get started with your bridge truss analysis. And then the last one will be just kind of going through the whole process of how you would do the calculate the forces. All right, so first thing that we need to understand is what are we talking about when we talk about bridge trusses? And really what we're looking at is all the beams. So a truss bridge is one that is made up of relatively narrow beams. We say narrow; they're not tiny by any means, but they are relatively small compared to the overall length of the bridge itself. So this is not going to be the same thing that you'd see with like a concrete bridge that you see on highways, things like that. This is more of a traditional truss bridge where you have steel beams that are connected together at corner points, and those vertices where they join together will be clamped together multiple different ways. A lot of them are going to be put together with gusset plates where they've got either a rivet or a giant bolt that's going to hold those things together. With that being said, there's really two main forces that we're going to look at. Now, there's actually a third type of force, which is shear force, that we're not going to look at. It's not the main one that we're looking at as far as beams. There definitely are shear forces that act on bridges, but they're not going to be on the main beams themselves too much with the part we're looking at. So two main forces we're going to think about are compression and tension. And so compression, as the picture is showing, is just going to be a squeezing force. So you're going to be pushing in on the beam from both ends. So anytime we push into the object, we're creating a compressive force. And so compressive forces hold up well if you have, sometimes a larger beam. You see that with concrete. Concrete's really good in compression, but not so much in tension. And so there's, different places where one type of material will be used better than the others. So compression is something that's going to happen in a bridge, and we have to kind of plan for that in the types of bridge trusses that we pick. Again, we're not going to get into all that here with what we're doing, but that is something that you'd be looking at. Is you need to understand whether it's a compressive force or a tension force, because that's going to affect what type of materials you use and what types and shapes of beams that you might be looking at. And then tension force, as the name implies, and as you can kind of see in the picture, is going to be one that's pulling on the ends. So things like rope and chain or any kind of cabling, we can put those things into tension, and they work very well under tension. They don't work at all in compression, because once you push on them from the ends, they'll just collapse. But as a tension carrying device, they work really well. So ropes and cables and chains, you see those in bridges quite often, especially suspension bridges, where they are supporting a tension load, but they will not be under compression. And so that, again, you got to understand what type of force you're looking at, so you know which type of material to use. All right, so we said, we're looking at truss bridges. And again, a truss is made up of, relatively slender members. They're going to be thinner than, the overall length of the bridge. But they're not tiny. They're very large steel beams usually. And they're going to join them at the end points of each of those pieces. And so, we said earlier, they're going to be welded together, or more likely gusseted together. And you can kind of see these little gusset plates here, that metal plate that's joining these different beams together. There's one up here. Those gusset plates are used to join them together. And so you can see there's a lot of bolts or rivets. I'm not sure which of those are. Probably bolts, but they might be rivets. And again, we're looking at simple trusses. We're not going to anything too complicated, because we need to be able to actually do these problems. So if it's a simple truss, it's all going to be triangles. That is going to be the number one key thing that we're doing. And that's not to say that you can't make more complex things, but for what we're doing, for us to be able to solve these problems, and really just to get to the basics of it actually working, triangles are going to work the best, because they have a very solid structure, but they're also very well mathematically defined, which help us to solve what we need to. So why pick triangles? Well, if you went for something like this, so here we've got just a basic rectangle, which is a parallelogram. If you apply a force to that, it's going to move. And of course, sometimes that's something you want. If you're wanting to make some kind of mechanism that can extend out, that's a good thing. But for a bridge, that's not something we want. And so what we're going to do is we're going to fix that by putting across a diagonal member. And that diagonal beam is going to allow us to keep that from moving, because we would have to bend that cross piece for this to change its shape. Because right now, in this picture, this diagonal is changing as that moves. So when that moves, the diagonal distance from here to here and the distance from here to here are going to change. By adding this cross beam, now we're fixing that diagonal length. So if that diagonal length is not able to change because that beam is holding it the same, now this becomes a much more rigid structure. So when I put a force on there, it is not going to move anymore. And that's generally the idea. We want triangle shapes because triangles are going to prevent us from having that rotational motion. All right, so the other thing we will look at is how do we support this bridge? And there are two different types of supports that we're going to look at. One is a pinned support, and pinned support basically just means that it's almost like putting a bolt through a couple of pieces of material to hold them together. So it's going to allow for rotational motion. If I put a bolt through something, it allows those two pieces to move and to pivot. But what it's not going to allow it to do is have them move in a translational way. So we can't slide it left or right or up or down. So when we pin something down to the ground, think of it as almost like a lever. And that's our fulcrum of our lever. So we're keeping it from moving horizontally, we're keeping it from moving vertically, but we're not necessarily preventing it from rotating. Now, obviously, with the bridge, we aren't going to want it to rotate in some very special instances. So we really won't be using that rotational ability, but it is not being kept from rotating. So that is the thing to think about. So when we say a pin support, it's going to support it in 2 dimensions. And why is that important that it's 2 dimensions? That means when we go to do our free body diagrams, we're going to have to put in 2 forces, one in the X and one in the Y, as potential forces that could be acting at that pin joint. So we're going to have some kind of force acting here to hold the bridge up, but the forces, if it's a pin joint, will be potentially in the Y direction vertically and also the X direction horizontally. The second type of joint we get is a roller joint, and the roller joint is really important in pretty much all bridges, especially with truss bridges. You don't see this the same way in concrete bridges. Concrete bridges have a different mechanism for this. They have an expansion joint where it kind of almost looks like a metal zipper thing across the roadway. So you might see something like that. But a roller joint is there to allow for expansion and contraction of the bridge itself, because as temperatures change, as things get warmer and colder, that metal is going to expand and contract. And as it expands and contracts, it's going to change the overall dimensions of your bridge. And if both ends are fixed and cannot move horizontally, then what's going to happen is your bridge is going to start getting a lot of stress fractures and small things that will lead to big things later on as that expansion and contraction continues over the years. And so this is just put there to kind of help prevent your bridge from breaking itself just as the temperature changes. So the roller joint is there to support your bridge in one direction only, and then allow it to move in another. And normally it's going to be this way where it's holding the bridge up, but it could certainly be on a vertical surface as well. So you might have something where that is keeping it from swinging left and right, but it is not necessarily keeping it from moving up and down. That's a less likely case, especially again for bridges. For us, it's going to be this case over here, the one on the left, where we are supporting the bridge vertically. So we are going to have a support force. When we draw on our bridge free body diagram, we'll have a support force vertically, but the roller joint will not have a horizontal one because it's allowing it to move that way. All right, so we've got some assumptions we're making, and these are all things that make the problem simpler. They definitely are ones that will make it somewhat incorrect. I mean, we are definitely putting in some error by doing this, but it's not terrible. And so these are one of those things where they're allowable assumptions with allowable error. Understanding that when you are designing things, you would also put in a safety factor and a margin of error that you would say, okay, well, if it is designed to withstand 100 pounds, then I can safely put, say, 50 on there. And I'm not going to go up there and say, okay, well, I designed it for 100, so let's put 100 on there. And because, you really haven't, I guess, accounted for any possible error that might be in there. So when we do this, all the forces we're looking at will be pretty accurate. However, we're definitely not looking at everything that's happening. And so we are doing this saying, okay, well, we know there's probably going to be a margin of error that you're going to have to account for when we do that. So our assumptions here are A, that we only use straight beams. So we don't have anything that's going to have a curve or an arc to it. Now, why is that? Because when we start having curves and arcs, you start putting stresses and forces in directions other than along the beam. So you start getting those sideways, shear stresses acting on here, which we are ignoring. So since we're not going to look at those, we are not going to deal with situations that would have them. We're also going to assume that all of our loads are applied at the joints, which again is not initially a true statement, but it definitely makes it simpler for us and allows us to actually analyze this bridge. So while, again, not necessarily a bad assumption, but not necessarily a realistic one. All joints are pinned and frictionless. Again, nothing's really moving, so the fact that they're pinned and frictionless shouldn't affect anything, but it's not necessarily true. Because obviously we said earlier that most of these things are either welded together or they're going to have bolts or they're going to have rivets that hold those things in place, so they're not going to be able to move. And so we're ignoring those forces that would happen if that happened. The one that's also a big one here is that we're assuming it has no weight. Each of those beams is weightless, and that's a big assumption, and that's one that's probably not realistic. Well, definitely not probably. It is not realistic. But the assumption is that the load that we would be putting onto the bridge is going to be much larger than the bridge weight itself. And so we're going to ignore the weight of the bridge. That's obviously not a good deal, but just keep it simple. We're going to go ahead and do that. And then because we said earlier, we're going to have only these perfectly straight members, we're going to assume then that we're only going to have tension or compression forces. And again, just keeping it simple, keeping it down to where we can actually work on these problems ourselves. So again, we talked about, what kind of risks we have. Obviously, you're ignoring some big things. And so there's definitely some forces that are acting that maybe we're not taking into account. So you definitely want to, think about adding in a margin of safety to whatever we're looking at. A couple of quick things. One of those is called static determinacy. All that really means is that this bridge is designed in such a way that we can actually mathematically solve the problem. If this is not true, if this equation does not work, then the bridge we're looking at, we will not be able to do the math. We're going to end up with too many unknowns and not enough equations to solve for it. So it's going to become an algebra issue. If you've ever done solving multiple variable equations where you have two equations, two unknowns, this is basically that situation. I have to have as many equations, as many options to kind of work through this problem as I have variables. And so if my bridge is not statically determinate, not going to work, not going to have enough information. All right, so the equation basically says this. You take 2 times the number of joints, and again, the joints are just the places where the beams are connected. So all your vertices. So you add 2 times the number of those vertices, those joints, has to add up to the number of members plus the number of reactions. And so the number of members part makes a lot of sense. That's just how many beams do you have. The number of reaction one is a little bit harder, but it's an easy concept. When we say a reaction force, what we're really talking about is the support forces that are holding up the bridge. So that's our 2 ends of the bridge. And we're not going to get anything that's got like a middle pier or anything like that where we have extra supports. We're just going to have one at each end of our bridge. And so it's either going to be a pin joint or it's going to be a roller. And generally what we're going to find for all of our bridges, and really most all truss bridges will be this way, is that there'll be 1 pin joint and 1 roller joint. So this R value should be 3. And the reason why it's going to be 3 is because that pin joint has 2 forces. We said because it's preventing motion in 2 directions, and the X and the Y, horizontal translations and vertical translations. That is 2 reactions, 2 forces. And then the roller joint has 1 because it is supporting the direction in 1. And neither one of them are restricting rotation, so we don't have any kind of moment to worry about. So when we talk about number of reactions, we're just really adding up those support forces. And again, for most of every bridge we do, that total should be 3. Now, could it be something different? It certainly could be, but realistically, most simple truss bridges that we'll look at will have a number of reactions that equals 3. So that R should probably be a 3 in every equation we look at. But it's just something you want to look at to make sure that what you're doing is going to actually be solvable before you spend a lot of time trying to work out the math of what the tension forces and compression forces are. And so here's an example of, is this bridge statically determinate? Well, what you want to look at is, well, how many joints do I have? There's 1, 2, 3, and 4, A, B, C, and D. There's 4 joints, so you'd have 2 times 4. And so you get 8 for this side. And you count, okay, well, how many members? And a member is going to be basically every point, or every line between these vertices. So we have 1, 2, 3, 4, 5. So M should be 5. And then we start thinking about, okay, well, what about our reaction forces? And so we got to look at our picture. And again, picture-wise, this triangle shape, that represents a pin joint. So right now we've got a pin joint at both ends. And we said a pin joint is 2 reaction forces because it's an X and Y horizontal and a vertical translational force. And so we've got 1, 2, 3, 4 reaction forces here. And so we get 5 plus 4 is 9. And this equation then doesn't work. We get 2 times 4, which does not equal 5 plus 4. And so the question is, well, how do we fix that? And so we need to change something. We don't really want to change the number of joints because that would change our bridge structure completely. We can't get rid of a member because we need those triangles. So our really only way of fixing this right now is going to be to adjust the number of reactions. And so, like I said, pretty much every bridge we look at is going to have 1 pin and then 1 roller. And that will make this reaction value 3 because we'll have 2 forces for the pin joint and 1 for the roller. So you'll see that that's the change we want to make, is we'll replace one of those pin joints with a roller joint, and now we can count everything up, and now we're going to have 2 here plus 1 there makes R3. So 5 plus 3 is going to add to 8, and then now we're good. And again, that doesn't mean this bridge is a good bridge or like, this is the best bridge ever. It just means that we can mathematically solve for all the forces acting on these beams if this is true. And so here's an example. You can count that on your own if you want to. We're not going to count it together, but here they're telling us that it has 19 joints, 35 members, and 3 reaction forces because at one end there's a pin and one end there's a roller. Can't really tell from looking at it which one's which, but one of them's a pin joint, one's a roller. And so just again, check the math and see, yes, that does add up. So this would be something you could mathematically solve. This is not something we'd want to do by hand because this would take forever, but it is mathematically solvable. This is pretty much what West Point Bridge Design does. If you've ever played with that, it's basically doing the same calculations that we're going to be doing. Obviously a lot quicker than we can do it by hand, but it does have the same issue. And that's why if you ever play with it, it always demands that you use triangles because it needs to be statically determinate. And so that's what we need to have happen to get this all to work. All right, real quickly, we're going to finish off with just the equations we're going to be looking at, and then we'll end this video. So what equations do we need to use? So we have 3 equilibrium equations we've talked about at different points in the year. The one that we talked about most recently, if you watched the previous video, was moments. And so our equilibrium equation says if we are in static equilibrium, the sum of the moments about a given point adds to 0. Well, what does that mean? That means I'm going to pick some point on my bridge as my pivot point, my point that I'm using as kind of the starting point for this moment calculation. And I know then that all the other forces acting on this bridge should cause moments that add to 0. Otherwise, my bridge would be spinning and accelerating, and that's not obviously not happening. So that's something we should be able to expect. Second one is the forces in the x direction. Our horizontal forces should always sum to 0. That's, again, assuming we're going to go through and find the x and y components of all of our forces, because obviously our forces are not always going to be acting vertically or horizontally. So if they're not, we're going to split them out into their x and y coordinates, or x and y components of those forces. And so some of the forces in the x direction have to add to 0, because what happens if they don't? Again, our bridge would be accelerating in the horizontal direction. That means it would be moving and it would be speeding up either to the left or the right. And that's not something you want your bridge to be doing. So when our bridge to be sitting still, then this needs to be true. And then our third equation we're going to deal with is the sum of the forces in the y. So our vertical forces same reasoning, have to be zero. Otherwise, our bridge would be accelerating. If our sum of our forces does not equal zero, that means it is accelerating. It is moving, and it's picking up speed either vertically or horizontally. In this case, it'd be the vertical one, and that again is not something we want our bridge to be doing. So, for our bridge to be sitting still, all of these things have to be true. The forces in the x direction have to add to zero. The forces in the y direction have to equal zero. And the moments around any point that we pick should add to zero. And if all that's true, then we've got a good statically determinate realistic bridge that we can analyze. All right, so we're going to end there, and we'll pick up next time with the next part of that. Thank you.